When you consider a Smith chart, you can see that it has two different types of curves. One consisting of red colored curves and circles and blue colored curves and circles. So these two different types of colored circles and curves consist of impedance chart and admittance chart. So in our previous videos, we have analyzed what is meant by impedance chart and what is the importance of impedance chart, how we can analyze different load impedance, how we can identify the reflection coefficient, transmission coefficient, VSWR using the impedance chart. So in this video, we are going to see what is actually mean by admittance chart, that is these type of blue circles and curves. So let's see. Let's have a quick overview on the impedance chart, which we have already discussed in our previous videos. So this will be our system, which consists of a source which is connected to the load through a transmission line, which will be having the characteristic impedance Z0 and the load impedance is ZL. When we have to plot this load impedance on the Smith chart, that is this impedance chart, we have to first normalize that load impedance with the characteristic impedance, and using the R and X value, that is the resistance and the reactance value, we have to find out that impedance in the impedance chart. So we have seen that these circles are known as constant circles and these curves are representing the inductance and the capacitance. So these portions above this line is the positive reactance or the inductance. You can see the value of this inductance here, and the portion below this line is the negative reactance or the capacitance. Here you can see the value of the capacitance. Next, let's see how the admittance chart is formed. So we know that the impedance is given by Z equal to R plus Jx, where these are the normalized values and R represents the resistance and X represents the reactance, which can be inductive or the capacitive. So in case of the admittance, it is the reciprocal of the impedance, that is Y equal to 1 by Z. So if you have to plot that on the admittance chart, it has to be normalized, that is y normalized equal to y by y0, which will be given by g plus jb, where the real part will be corresponding to the conductance, which is the 1 by r. So this will be the conductance and 1 by x will be the susceptance. So these are plotted on the admittance chart. So let's see how it is formed from the impedance chart. So here it shows how the Z to Y transformation is happening. So this shows our impedance chart. Here you can see that the constant circles and these curves represents the inductance and the pink curve represents the capacitance. So when we are taking the inverse of the impedance, it is like rotating 180 degree. Sorry. So it is like rotating 180 degree. So now we can see that when it is getting rotated, the negative J value is coming on the top and the positive value is coming below. So in the admittance chart, the axis above this is negative and the below is positive. So let's see that in more details. So here this will be the admittance chart and these circles will be the constant susceptance, constant conductance values. So these circles will be the constant conductance, similar to the constant resistance in the impedance chart. As it is taking the 180 degree reversals, the top portions will be representing the negative susceptance or the inductive values, and the below portions will be the positive susceptance or the capacitive value. So let's see how the negative susceptance is corresponding to the inductive value. We know that when we are considering the inductance, the impedance is represented by Z equal to J omega L. When we have to consider the admittance, we have to take the reciprocal of 1 by Z. That means that 1 by J omega L. So 1 by J will be equal to minus J by omega L. That is why this negative susceptance is showing the inductive value, and that is what we are seeing on the top portion. Similarly, in case of the capacitance, Z is given by 1 by j omega c, and when we consider the admittance, it is the reciprocal of 1 by Z, then it will become j omega c. So the admittance is, when the admittance is positive, it represents the capacitive value. So the capacitive is happening on the below portion. So it is just the reversal of the impedance chart. So this is how the admittance chart is looking. So the negative susceptance will be inductive and positive susceptance will be the capacitive part. So which will be represented on the below part. So let's see how these admittance are plotted on the admittance chart. So if I have a normalized admittance chart like 1 minus 1j, this is the normalized one. So if I have to plot this on the admittance chart, first what we are doing is we have to find this one is the real value which will be corresponding to the conductance. So these circles will be corresponding to the constant conductance. So I have to find the circle corresponding to the value 1. So here you can see that this circle is corresponding to, so this circle is this circle. So here you can see that the value is 1. This circle is corresponding to the value of 1, and it is minus 1j as it is the susceptance. Minus represents the inductive value. So it is on the top. So this one represents the inductive value. So this line will be minus 1j. So the intersection of both this will be representing 1 minus 1j. Similarly, if it is 1 plus 1j, this plus 1j represents the capacitive value. So if we have to represent this on the admittance chart, first find out the constant conductance circle and find out plus 1j. So this is the capacitive value corresponding to plus 1j, and the intersection will corresponds to this value. This is how we are finding the normalized admittance value in the admittance chart. So in a complete Smith chart, we will be having both the impedance chart and the admittance chart. So the impedance chart will be represented by these red colors and the admittance chart will be represented by these blue colors. So these impedance and admittance chart has very importance in designing these matching circuit. So while designing the matching circuit, we have to use the inductance, capacitance, which can be in series or in parallel configurations. So if we have to find out the equivalent impedance when we are adding a series or capacitive inductance to capacitive loads to that, to find the equivalent impedance, we can use the complete Smith chart. So let's see how it is done. So this is our common circuit which will be having a load impedance and the which is connected to the source through the characteristic impedance Z0. So let's consider the scenario if I have to add an inductor in series to the load impedance. So here you can see that an inductance is added in series to the load impedance. So in that case, if we have to find out the actual equivalent input impedance, we have to consider the impedance chart. So for that, what we can do? So let's assume that if our load impedance is 1 plus 1j, first of all, what you can do is we have to find out where this 1 plus 1j comes. So let's see that where it is coming. So as it is ZL equal to 1 plus 1j, what I have to do is I have to find out the constant resistance circle. So here you can see that this plus 1, this is the constant resistance circle, and what I have to do is I have to find out plus 1j. So the plus 1j is, this is the plus 1. So I have to find the inductance. So this intersection will be representing 1 plus 1j. And my task is to add an inductance of 0.5j to this value. So if I have to add 0.5j inductance to this value, what I can do is this is my constant circle, right? So if I have to add an inductance to the series, you can move along this constant circle by 0.5. So here you can see that as my total inductance is 1, when I move with zero point 0.5, it will be 1 plus zero point 0.5. So total will be 1.5. So in this constant circle, I have to find the inductance value which will be corresponding to 1.5. Here you can see that this is 1.2, 1.4, 1.6, like that. So this will be corresponding to 1.5. So this point will be my equivalent impedance value after adding the inductance. So here you can see that this is how it is done. So if we have the load impedance, if we have to add zero point 0.5, just move to that point where the value of the impedance will be 1.5. Here you can see that the impedance is 1.4 here, and this is 1.4, this inductance is 1.4, and this inductance is 1.6. So this line corresponds to 1.5. So the total inductance value is 1.5. So this value represents the total input impedance if we are adding a series inductor. So let's consider the case if I have to add a series capacitor like this. So if I have to add a series capacitor, what I can do is, if I know the load impedance, first of all, what I can do is I can mark the load impedance there. So now in my case, the load impedance is 1 plus 1j. So this load impedance is 1 plus 1j. So first of all, I'll be marking that. So first of all, I will be considering the constant resistance circle and plus 1j. So that intersection will be 1 plus 1j. So my task is now to add a series capacitance. So if I have to add a series capacitance, its value will be, means I am considering the value as minus 0.5j. So here I am adding a capacitance of minus 0.5j. So in that case, my total impedance will be 1 plus 1j minus 0.5j. So that will be 1 plus zero point 0.5j. So adding a series capacitance of minus 0.5j means I have to move by 0.5 along this inductance. So here my inductance is, initial inductance is 1j, and if I have to move by minus zero point 0.5, that means it will be 0.5. Here you can see that it's zero point 0.9, 0.8, 0.7, zero point 0.6, and zero point 0.5. So this line will be my 0.5 inductance, and that intersection of the constant resistance and this line will be my equivalent value after adding the series capacitor. And let's see what is the relation between the impedance and admittance chart. So in our previous analysis, I have considered an impedance of 1 plus 1j. So uh, if I have to mark that, I have to consider a constant resistance circle whose value is 1, and the inductance value which is also 1, and that intersection will be corresponding to 1 plus 1j. So if I have to find out that admittance, corresponding admittance, what I have to do is I have to consider the blue chart. The admittance corresponds to the blue chart. So if I have to find the admittance for this point, I have to I have to consider the blue chart, and this is my constant conductance circle. So I have to draw this constant conductance circle, and this constant conductance circle value is 0.5 here. So it corresponds to 0.5, and this blue line is my inductor now, means uh, susceptance now. So this will be corresponding to 0.5 here. So if I consider the blue line, blue circles and the lines, I'll be getting the corresponding value. Sorry, I'll be getting the corresponding value. So here you can see that the constant conductance is having a value of 0.5, and this blue line is also having a value of 0.5. As this blue line top portion is negative, this admittance value is 0.5 minus 0.5j. So this is my admittance. So let's see what is the importance of admittance chart. So in our previous slides, we have seen that if we have to add a series, inductance and capacitance, we can use the impedance chart. But consider the scenario if we have to add a parallel inductor. What we can do is, instead of using the impedance chart, we can use the admittance chart, because we know that when that inductor is added in parallel, the total input admittance can be calculated easily using the admittance, because it will be the sum of both the load admittance and the newly added admittance. So if we consider the admittance, it is very easy to calculate the total input impedance. So in that case, we can see that uh, like if we have to find out the total input impedance, we have to just use the admittance chart. So sorry, these are input impedance. So the total input impedance can be admittance can be given by this expression. So consider an example. If I have a load impedance of 0 minus 0.5j, and if I have to add an parallel inductor of minus 0.5j, I have to find the total input impedance. So let's consider the scenario. So if I have to find out that on the admittance chart, what I can do is I can take the constant conductance, that is the blue circles. So this is the 0.5, and this line is also the minus 0.5. So this is our load admittance value. So next what we have to do is we have to add a parallel inductor of minus 0.5j. So if it is like minus 0.5j, we have to move upward. So if we are adding a parallel inductor, we have to move upward. So as it is minus 0.5, it is like moving to more zero point 0.5. So we have to like move to zero point 0.5, and the total, this is the one value. This line is the one value. So I have a constant resistance circle and a constant conductance circle and minus 1j. So this will be this will be my new input admittance. So if you have to add a parallel inductor, just move on the admittance chart. Similarly, if you have to add a parallel capacitor, what you have to do is you have to move downwards. So if it is like adding a capacitor, it is like moving downwards on the constant conductance circle. So this is my case. Like this is my load impedance 0 minus 0.5 j, and I am planning to add a capacitor of 0.1 j. So I have to move 0.1. So here you can see that as it is minus zero point 0.5 plus zero point 0.1, the total will be 0.4. So this line corresponds to 0.4, and that intersection will be my new input impedance. So these are input impedances. So this is how we are calculating the total input impedance if something is added in series or parallel. That means that if we are adding something in series, we have to use these impedance charted. So if we are adding a series inductor, you have to move up, and if we are adding something some capacitance in series, you have to move down. If it is a parallel inductance, you have to use the admittance chart, that is the blue chart, and you have to move up. If it is a parallel capacitor, you have to use the admittance chart and move down. So if it is series, always use the impedance chart. If it is parallel, always use the admittance chart. So that is the importance of impedance and admittance chart in Smith chart. So I hope you get some idea about what is meant by impedance and admittance chart, and how you can identify the total input impedance uh, if an inductor or capacitor is added in series or parallel. Thank you.